Okay, we're going to go ahead and get started this morning. This is a new session to AGU. This is the Union Education Tutorial session, the first time we've done this, and that may explain some of the little bumps and bruises that we're experiencing along the way. One of the things you may have noticed is, although this appears on page 3 of the volume, it doesn't appear within the regular schedule, and so we had some missteps here in trying to get this in the schedule, and that may be responsible for some of the other things that will go on today. One of the issues we have is we're trying to get presentations set up, and there are some issues there. So if you see a lot of audiovisual people running around, my apologies. We'll try to do a better job on that next time. The goal of this session is to try to provide a service to the membership as well as to educators, students who may not have already joined AGU, and the press, frankly, to provide them a chance to get some background overview information on major research areas in the geosciences. The sessions that have been, or the topics that have been selected for today are major research topics in the geosciences and are associated with sessions at the meeting that you can continue your interest that may be initiated at this session in further research-focused sessions later on in the meeting. We've invited 4 speakers who are known for their public speaking abilities to be able to make these presentations, and we're very appreciative that they agreed to do these tutorials. I'll make a few introductory remarks prior to each presentation so you'll know who's speaking to you. And in order to finish on time, I think we will allow 23 minutes for the presentation and 5 minutes for questions and changeover. This was a suggestion from CEHR a couple of months, or well, nearly a year ago, in fact, to put this idea together. It was received very positively by the meeting program committee, and we would be interested in receiving comments about this session and its usefulness. When you fill out your form, your evaluation form from the meeting, that would be very useful to us. So please, if you fill that out, we encourage you to do so. Make some comments about the session and whether you'd like to see it continued, expanded, and so forth. Our first speaker is Barbara Thompson, who's going to be speaking to us on solar variability. Barbara received her PhD in physics in 1996 from the University of Minnesota. She did her thesis on numeric modeling of Alfvén waves in the inner magnetosphere. She began working at Goddard in 1996, working on SOHO, and joined the solar physics branch in 1998. She's currently involved in operations and development of several solar satellite missions and rocket programs. Barbara, are you set?
Yes, thank you.
All right.
All right, I was hoping I wouldn't have to speak at the podium because, as you might imagine, I have trouble seeing over these things. They're usually made for, I think they make it for an average type man, and I'm kind of stuck when it comes to that. I thank you for coming. I hope that the items I've selected for this tutorial are appropriate and will assist you in your understanding of these talks here at AGU. As you can imagine, there's a lot of things that are covered, and 30 minutes is going to be a relatively short amount of time for me to give you a good introduction for things. However, I thought I'd focus on a couple of points that people often get stuck on in our field and try to at least give you a fighting chance when you start to go in these sessions. I'd also like to thank the AV people for letting me hook up my computer. I guess we're not allowed to use the projectors anymore, and I apologize for any confusion this might have caused. It would be horribly embarrassing now if my computer managed to crash in the middle of this thing. Oh, that would be wonderful. All right, now I can see people better. I thought I would try to give you a background to make up for some of the deficiencies in some of the talks. A lot of the talks are only given 15 minutes, and that's not enough time to provide a background and context in the state of the research, as well as a discussion of your own research. And so I will take advantage of this tutorial time to be able to try to give you a little bit of a background on some of the driving questions. So first of all, I have to start with a summary of the sun, its structure, and how it works. Because if you don't know how the sun works, you're not going to understand deviations from how it's working in the form of solar variability. Second of all, I'll go to explicit phenomena and terminology associated with solar variability. There are a lot of different things which cause solar variability, and these will be discussed at great length in a lot of the sessions here at the meeting. Finally, if I have time, I'll discuss a little bit of the stuff that's going to be going on at the special sessions and some of the general sessions, because those are things, if you're particularly interested in solar variability, you might want to check out. All right, the sun is 5 billion years old. I'm going to try to cover this in 5 minutes. Let's see how that goes. The sun's an extremely variable magnetic star. Now, I want to make sure that you realize it's not an extremely variable star. In actuality, it's quite a typical star for a star of its class, the main sequence stars. However, it exhibits a great deal of variability if you happen to be a person living on a planet which is pretty close to it. And most of the variability has to do with the magnetic field of the sun. So we call it an extremely variable magnetic star if you're here on Earth, and you call it a typical star if you're an astronomer. So we're going to be geophysicists, and we're going to call it very dynamic and variable. For all the ways that the sun contributes energy to Earth, and I'll go over a lot of them, each way that the sun contributes this energy to Earth exhibits fluctuations which may have measurable impacts at Earth. So that's quite interesting because there are a lot of ways that the sun influences Earth, and solar variability takes so many forms, and the Earth system is so complicated that there's quite a few impacts as well. So the source of the sun's power is nuclear burning in its core. Every second, the sun turns 4 billion tons of hydrogen into energy. It produces these photons, which then travel to the sun's surface and become what we call the photosphere, the sun's bright visible surface. It takes a photon about 170,000 years to travel from the sun's core to the sun's surface. Now, if it takes on average that much time, that means that variability of the core on timescales that are shorter than that will be very difficult to detect. In other words, variability of the sun, which is on human timescales and even on the timescales of millennia, probably does not originate at the core. It originates in a more dynamic portion of the sun, which we call the convection zone. In between the core and the convection zone is what we call the radiative zone. And I think, I guess I'll use my, is there a way to point? I guess not. What you'll see is in between, okay, sorry. I haven't thought of getting a pointer. Anyways, the core produces all the energy, and the light travels through the radiative zone, and the convective zone are those little cells you see on the outside, and they're just like cells in a boiling liquid. Well, thank you very much. These cells, in their motion, cause the magnetic field of the sun. It's what produces the plasma of the sun. We call it the solar dynamo, and it actually involves a lot of interior flows of the sun. The sun's interior is flowing at different speeds, and there's also convection going on, and the flow of this plasma is what produces the dynamic magnetic field of the sun. Now, any deviations you see from a simple sphere will be because of fluctuations in the sun's magnetic field. A sunspot is a dark region on the sun which is associated with an extremely strong magnetic field. Something we call a prominence is some cool plasma suspended in the sun by the sun's magnetic field. And finally, the sun's corona, which is the extended atmosphere of the sun, is the expansion of the magnetic field out into what we call the solar wind, and finally into the heliosphere, which is the domain of the sun's influence. The dynamo, simply, this is just an animation, works by, you have magnetic field in the sun, and these flows, if you have a simple dipole field, the flows will produce a wrapping up of the magnetic field, because the sun does not rotate as a solid body. It rotates actually what we call differentially, different speeds throughout different latitudes and depths within the sun. So you have the building up of magnetic field, and even though this is just a cartoon depiction, what you're seeing happening there is actually quite accurate. You have inhomogeneities that build up and instabilities, and it causes the sun's magnetic field to emerge in little clumps. And it's these fields which emerge and become eventually the sun's corona, and again extending out into the heliosphere. Now, this process, as you can see, is not a constant process, and it's not a homogeneous process. Most of the features you see in the sun are because of the variations in the magnetic field, and each time the sun undergoes a process like this, it's slightly different, or it can be drastically different, actually. It's important to note that the magnetic field fluctuations are linked to all of the significant variations in solar energy input we receive at Earth. They may not be the cause, but they're definitely linked to the variations. There are a lot of different types of energy which reach Earth. First and foremost, of course, is just visible light, electromagnetic radiation, and that has mostly direct input to the systems on Earth, either the atmosphere or the ionosphere or the Earth's surface, that they influence. There's also, again, the flow of plasma and magnetic field through what we call the solar wind. This picture is just kind of a depiction of the different types of energy reaching Earth. I should say, in case people are really new to this, that this is not at all to scale. The sun is not right in our front yard. The Earth is 200 solar radii away. It's just very difficult to depict our Earth's teeny little magnetic field here in the context of the sun's extended heliosphere. In reality, the Earth would probably be out in the street over there. Okay, so this is kind of a diagram which shows how the sun's energy affects Earth. And again, the solar dynamo is the root of all solar variability because it's what produces the magnetic field and is typical for the interior flows which vary in the sun. The solar energy outputs consist of solar irradiant energy. First of all, visible light and infrared energy are very dominant, but extremely energetic wavelengths like X-rays and extreme ultraviolet radiation can dominate some processes on the Earth. In addition, we have energetic particles, solar wind plasma, and magnetic field which come from the sun. Now, if you watch how the energy deposits itself, you can see that it's not a direct process. The Earth is an extremely complicated system. Variability on the sun often doesn't have a simple answer at Earth or a simple reaction at Earth. What you'll get is you'll get input from X-rays to the thermosphere or the ionosphere, and that'll interact with the mesosphere while the X-rays are also interacting with this process. And you can see that a lot of these processes involve interactions in Earth systems as well as the sun. Additionally, I'd like to note that external sources of energy, actually cosmic rays don't contribute much energy, but they're important for other processes which I'll describe later. They come from outside the sun, but they come from interstellar space, but these cosmic rays, their impact and their reaching Earth is modulated by the sun's magnetic field. So the cosmic ray flux received at Earth is an indicator of the sun's magnetic field strength. Okay, I'll warn you, when you go to talks on the sun, people will show you pictures of very different suns. There will be colors that typically you don't think of as the sun, and they'll look very different. And it's the same sun, it's just that the sun has so many layers and has so many different facets of what we call faces of the sun, that it can look very different. Almost all images of the sun will be false color. We just color them, we just assign them a color often because, for example, this is an X-ray image of the sun, and you can't see X-rays, so we color them red so we can see them better. And with X-ray images, you can actually see the extended corona a little bit better. You can see the magnetic loops, which are associated with sunspots. That's a hot region. It's in millions of degrees. As you get closer to the sun's surface, you'll see what we call the chromosphere, which is right above the visible surface of the sun. That you can see in the ultraviolet and the extreme ultraviolet. And again, you can see it's extremely patchy. All of these patches are due to changes in the magnetic field. And finally, in the visible light, it more resembles the sphere that we think of as the sun, with a couple of sunspots. Now, I'm going to show you a movie. This image right here is a magnetogram, which is another type of image of the sun. People will also call it a magnetograph or magnetic field image of the sun. And white denotes magnetic field coming out of the sun, black denotes magnetic field going into the sun. So you have kind of a loop forming right there. And when it's very strong, it forms a sunspot. So what this movie is going to do is it's going to advance through a bunch of wavelengths on the sun to show you how different they look. So there's your sunspot. You go into the extreme ultraviolet, then finally to X-rays. And it'll loop through. Watch how after a while you can't see the sunspot because you're not looking in visible light anymore, but you start to see strong magnetic field loops coming from it. Again, a very inhomogeneous structure, and it looks very different depending on how you're looking at it. All right, I'm going to do a drive-by glossary of the of solar variability type terms because I think they each deserve a little bit of time for people to maybe understand their significance, but also what kind of questions we're trying to solve with them. So first and foremost, of course, involves the solar dynamo again. The solar dynamo is responsible for what we call the 11-year solar cycle. That is a series of fluctuations whereupon we go from solar minimum to solar maximum in magnetic activity. It's also called the 22-year solar cycle because during this cycle, the solar magnetic field flips. If it goes from an essentially bipolar at solar minimum, it becomes very active at solar maximum, and then at the next solar minimum, it's an opposite bipole. So some people call it the 22-year solar cycle. But I must emphasize that the sunspot cycle itself varies quite a bit. And so it's difficult to call it even a 22-year solar cycle because it does not return to its original configuration at the end of that cycle. So most of us still call it 11 years. This is a plot of the sunspot number in recent centuries. And you can see the modulation right there. That's an 11-year periodicity. It's very easy to pick out. The sunspot number is an indicator of how active the magnetic field of the sun is because magnetic fields cause sunspots if they're strong. And the sunspot number is an indicator of how many sunspots there are and also how strong and large the sunspots are. It's nice because we have a long record of sunspots that have lasted for about 500 years now. You can see I guess a little over 400 years. Anyways, you can see that even though there's an easily documented periodicity of 11 years, the difference between solar minimum and solar maximum can vary quite a bit. And in particular, you can see this region we here call Maunder minimum, where there's evidence that the number of sunspots even during solar maximum is quite small. The sun went through a relatively dormant period. And this is recent enough, this is the late 17th, early 18th century, for us to have historical records of some of the effects that the Maunder minimum might have caused, which I'll get into a little bit later. So you can see that the solar cycle has an obvious impact on solar activity, but there's long-term trends which are also extremely important. In addition, there are also short-term trends. All of the types of energy which impact Earth vary with the solar cycle. However, all of these types of energy vary more drastically on shorter time scales. Whether you care depends on what you're trying to study. If you're trying to study a system at Earth that is driven by the 11-year cycle because the processes at Earth take about 11 years, then you'd be concerned with the solar cycle and long-term behavior. However, a lot of short-term processes are important at Earth as well. The solar cycle is also called the sunspot cycle because that's how we originally documented its variation. And again, the magnetic cycle because it's really the magnetic fields which cause it. As I said, everything varies with the solar cycle to some extent. An example is the solar X-ray flux. You can see the 11-year periodicity here. This is just a couple of decades. However, X-rays in a couple of minutes can vary by many more orders of magnitude, which is very interesting because, again, depends on what you're trying to study. If you're trying to study the stratosphere and processes which are driven on a more steady flux, longer term, the middle UV, even though it only varies by 8%, you might be concerned with the solar cycle. But the X-ray flux, and if you're concerned with regions which heat up rapidly, you might not be so worried about the solar cycle because you can see these quick peaks, typically 200%, and again, which can reach many orders of magnitude, may be the dominant things that you're worried about. Right? Solar radiance is the main source of the Earth's energy, light reaching Earth. And it's documented in a variety of ways. When people talk about total solar radiance, they're mainly talking about visible with infrared and ultraviolet. However, there are other irradiance studies which involve certain regimes. They'll call it X-ray irradiance and UV irradiance. And this is important depending on the process at Earth you're trying to study. We're kind of fortunate that the regimes which contribute the greatest amount of energy to Earth vary by the least fractional amount. But the converse is also true. The regimes which contribute the least amount of energy to Earth vary by the greatest amount to some extent, And interestingly enough, if you're studying the ionosphere and where you don't really worry too much about visible light, but if you're worried about X-rays and the extreme ultraviolet, this can be very significant. Okay, I should note that just so you get an idea of scale in contrast to the X-rays, which can vary greatly, the total irradiant energy input to Earth varies by far less than 1%, typically 0.1% over a solar cycle. And if you take that to be the primary source of heat at Earth, then you realize that that can't cause too much of a change at Earth. It's way less than a degree of change of temperature at Earth if that's just the direct input. So it gives you an idea of the complexity of how the solar energy reaches Earth and how it is retained here at Earth to determine the actual climate here at Earth. There's short-term variability, but again, there's long-term variability, and I won't go over this too much because there's a special union section on this. There's a lot of neat evidence of what we call cosmogenic isotopes. Those cosmic rays I mentioned earlier, they come from outside the heliosphere, but again are modulated by the strength of the sun's magnetic field. They can serve as a record of the sun's activity over very long time scales in things like tree rings and ice cores. And you can see there's a series of possible maxima. They've inferred the sunspot number based on recent records, and there are examples of maxima and minima in the sun's long-term variations as well, which are quite interesting. Okay, here's a couple of types of phenomena that cause the short-term variability. Flares, most people have heard of them. Unfortunately, they undergo kind of an identity crisis. People who talk about flares can mean a variety of things. In general, if you hear the word flare, you're dealing with someone who's seen a short-term, meaning minutes to hours, increase in flux in a small region of the sun, typically small compared to the solar radius, in any wavelength. So some people talk about white light flares, some people talk about X-ray flares, and flares are embroiled in another phenomenon called coronal mass ejections because both of them involve a very dramatic release of magnetic field energy. Again, the storage and release of magnetic field energy are very important facets of the sun. On the right there, you see what we call a coronagraph. That circle is the size of the sun. We've blocked out the sun because it's so bright and we can't see its extended corona and the sun at the same time. This distance is about 1/6 of the way to Earth, and what you see is the solar wind, plasma flowing out away from the sun, and if you look, you can't find anywhere where it's not at least a little bit variable, and mostly everywhere is disturbed at some point. Those large eruptions, right there and right there, are large loops of magnetic field being ejected from the sun. So both are processes which involve the liberation of magnetic field. And I feel like the difference really is if you take a rubber band and you stretch it on your lip, you can feel it heat up and cool off. And that's kind of like a flare. You're liberating the tension in the rubber band, and its energy is being released in the form of heat. But you can also just shoot the rubber band away from you, and that's like a coronal mass ejection. It just gets rid of this magnetic flux. But again, they're quite embroiled. So even though the irradiant input is a very important contributor of energy to Earth, the solar wind, what we call a tiny fraction of the energy input to Earth, can dominate a lot of processes. I know this looks like a piece of breakfast cereal. Be patient with me. You have an eruption, and that can travel through interplanetary space, carrying a lot of plasma, momentum flux, and magnetic field. And those things together can cause dramatic things at Earth because the Earth is surrounded by a magnetic field. So it's like fighting fire with fire. Here we have a model based on actual data. This is a simulation. That little teeny dot in the middle there is the Earth. And as you watch, the Earth's magnetic field is buffeted by the solar wind all the time, but here comes an eruption. And you can see a great deal of change happening. So you can imagine if you're a satellite or maybe an astronaut out there, you're dealing with an extremely variable environment. And we never know sitting here at Earth. Often the only real tangible immediate thing that we can sense is the aurora, which they kind of have mapped here. That's an indicator of how much the Earth's magnetic field is being impacted by the solar wind and transients in the solar wind. So I want to quickly give you an overview of some of the special sessions you might want to hit. Sun's a neat system because we study it for a variety of reasons. First of all, it's a great opportunity to study extreme environments that we can't reach at the lab. It's a natural laboratory for high-energy physics, and it's also a great place to learn about nuclear physics. A lot of breakthroughs in nuclear physics have been based on trying to understand how the sun works. We also likewise seek to increase our understanding not just of physical phenomena, but of astrophysical phenomena. We can learn a lot from other astrophysical phenomena by studying our nearest star. It's 93 million miles away. It's not so close, but it actually is close enough for us to be able to do actual physics instead of just observational astronomy on it. Finally, the reason I study the sun, and the reason why a lot of people find it interesting, is that the sun's variations affect Earth and Eurospace in a variety of ways. Not that people don't find astrophysics interesting, but here at the American Geophysical Union, I think people often emphasize the impact on Earth. All the special sessions, I'd say, cover at least two of these aspects, and I would say that really they probably cover all three. A lot of them do. So you're getting a great opportunity. Special sessions are a place where you focus on specific problems. So ones you might want to hit involving solar variability, first of all, there's one called the Earth's Interactions with the Sun from Millennia to Minutes, which will really discuss a lot of the sun's variability and its effects. And I find it interesting, again, the long-term solar variability and the paleoclimatology that people do to understand how the sun's been behaving. If you like the eruptions and the flares and things, you could hit the high-energy session. Often these things happen so quickly, and there's so much energy released that there's many manifestations. It's very difficult to disembroil all of these things. For example, you'll have shocks, energetic particles, flaring material. You have all sorts of things happening all at once. And there's been recent observations on how the magnetic field, when it's violently releasing the energy, has manifestations and effects. There's a session on interacting CMEs. Coronal mass ejection can have a strong impact on Earth, but if you get a second one catching up with it, not only do you have a complex heliosphere that's going on, but you're also dealing with complex effects at Earth. And finally, shocks and shock manifestations over the solar cycle. We'll cover a lot of these things together because shocks are a manifestation of energetic phenomena. You can also hit the joint sessions. We take advantage of being part of the American Geophysical Union. And the general sessions are interesting because you have people who have to give sometimes a little bit better introduction because they can't assume the previous speaker is talking about that. Finally, if you want to really learn about a topic, I'd suggest hitting a poster. There's nothing like getting to sit down with the author and talk about things. So I will, in summary, the sun is an extremely variable system. Again, not too variable for a star, but it varies in almost every context that we might be concerned with, being people here at Earth. The source of the energy is the core, but the root of the variability is the magnetic field of the sun. The primary source of energy to Earth is the radiant energy, and the light which reaches Earth varies on almost every measurable time scale. However, the magnetic field of the sun, which extends out into the corona, forms the solar wind and the heliosphere. That varies quite a bit as well. Three-dimensional heliosphere is an extremely complicated environment in which the Earth lives. Short-term variations are related to the magnetic field. Long-term variations are linked to the solar dynamo, which are also part of the production of the magnetic field. The short-term releases of energy have to do with the magnetic field, and flares and coronal mass ejections are good examples of those. So to wrap up, energy from the sun varies in a variety of ways, and all these ways are important. It's kind of an arrogant thing to say, but it's also an interesting field to study because you never run out of things to look at. There's evidence of solar variation in every type of way the sun impacts Earth, and there's measurable effects at Earth that we're uncovering, which also vary with the sun. However, people usually after seeing the evidence of the sun's long-term variability start to be very concerned. And I want to remind you that, again, the sun is not particularly variable for a star, but also it's not particularly variable compared to our species. It's really our changing technology and our reliance on this technology that's caused the sun to seem so variable to us. And sure, there are climatary effects, but most of the times people will see when people discuss maybe potentially a migration which was influenced by the sun's behavior, you realize that most of the migrations in human history have to do with either social interactions or technology development. So the species is varying a lot more rapidly than the sun. As we develop technology which is influenced by the sun, we also develop means of coping with the sun, which varies. So far the humans are winning. The humans are far outpacing the sun in their variability. So when you think about the variable sun, just enjoy it and find it an interesting system to study, and don't worry so much about the impact it might have on you and your family.